Today, we'll dive into icons, a gradient-driven influence consensus approach for vision language data selection. It trains VLMs using just 20% of the data, while still achieving 98.6% of the performance of the full data set. Let's jump in and see how less data can do more work.
Visual instruction tuning often relies on large amounts of training data for vision language tasks. But this can be inefficient when the data contains repetitive or redundant information. That redundancy drives up computational costs without improving performance. To tackle this, the paper introduces a method called icons, influence consensus for vision language data selection. How does it work? Essentially, icons uses gradient-driven influence metrics to see which data samples are consistently important across multiple tasks. If a particular piece of data is influential in more than one task, it's likely a strong candidate for the final subset. A majority voting system then pinpoints the most broadly valuable data. This means icons can train on a much smaller, high-impact subset rather than a massive, repetitive dataset. Look at the figure here comparing icons to a baseline dataset, lava-665K. Icons cuts the dataset size significantly, while maintaining or even improving accuracy on benchmarks like text VQA and VQA2. So the key point is efficiency without sacrificing performance. Visual instruction tuning is crucial for multimodal language models because it helps them interpret visual content and respond to language instructions. The challenge is that current methods often depend on huge datasets, like Lava's hundreds of thousands of examples, which leads to large storage demands and slow training cycles. This makes quick iteration difficult. We need a smaller subset of training data that can still maintain strong performance. Some sampling techniques focus on single-task optimization or only aim for diversity, missing the bigger picture of multitask performance. Icons addresses this by combining influence measures across several tasks. It uses a voting mechanism to find data samples that are universally beneficial, ensuring broad capabilities while keeping the dataset compact. The icons approach zeroes in on selecting the most impactful training data for vision language models. It leverages gradient-based influence estimation to see exactly how each training sample affects task-specific performance. The twist is the consensus mechanism samples. This mechanism relies on majority voting across tasks to pick out samples that consistently offer value everywhere. Although calculating these influence scores can be expensive up front, it's a one-time cost. After that, you're left with a compact, high-quality dataset that makes future training faster and easier. Using icons, the authors managed to pick just 20% of the Lava dataset while preserving 98.6% of the original performance on key tasks. In fact, this subset beat random sampling of the same size. It's a neat balance between efficiency and effectiveness, getting rid of redundancy but still covering all the tasks you care about. Here, we see the main contributions of icons and the framework for estimating data influence. The standout feature is the voting-based aggregation that puts a spotlight on training samples with broad value. Icons consistently outperforms other data selection approaches, and at a 60% selection ratio, it can even surpass the full dataset's performance. The Lava Icons -133K dataset, built using this approach, is much smaller than the original, but keeps almost all the performance. It even does well on unseen tasks, making it handy for efficient multimodal training. Under the hood, Icons uses gradient-based metrics to figure out each sample's relevance, focusing on how much it affects validation loss. That helps ensure the chosen data transfers well across multiple tasks. In this part, the authors break down how Icons processes training data in two main stages: specialist and generalist. The specialist stage deals with each task individually. First, it does a warm-up training using a small slice of data to fine-tune a base model. Next, it calculates gradients to see how each training sample impacts validation performance for that particular task. Finally, it averages those impacts to get influence scores, building what they call an influence matrix for the task. Then it repeats all that for the other tasks, one by one. Afterward, the generalist stage comes in and merges all the influence matrices from the tasks. For each data sample, if its influence score is above a threshold, it gets a vote. Samples, with the most votes across tasks, in other words, the top 20%, are chosen for the final dataset. That's how Icons ensures a tight but powerful subset that works well across many tasks. To compute the influence of training data on task performance, this section discusses an influence score. It measures how much updating the model with a single data sample affects the loss on some validation point. The authors use a gradient-based approximation to keep things relatively efficient for large datasets. In practice, they compute this influence score during a single epoch of training, but it can also span multiple epochs if you sum the effects. They rank samples by their importance after a short warm-up phase that uses just 5% of the data. The gradients for both training and validation samples are then computed and compressed for efficiency, which helps to figure out how each sample influences performance in a straightforward way. The framework continues by detailing how the influence consensus method aggregates these gradients. First, it calculates gradients for both training and validation data points to capture their interactions. To save time, the gradient features get compressed via random projection, and they also get normalized to handle different sequence lengths. Next, we see the influence matrix, which shows how each training sample affects validation performance across tasks. For each sample, they compute the average influence per task, rank all the samples, and then select the top ones for the final model training. Because it's a consensus-based selection, samples that are useful for many tasks win out over those that help only one or two tasks. Finally, the authors highlight that this process can scale to large datasets and adapt to new tasks without redoing all the gradient computations from scratch. That makes it practical for ongoing learning scenarios. Continuing on the theme of ranking and selection, this section dives into how Icons uses a voting-based strategy. Each task picks its most influential samples, and then Icons aggregates those choices to find data that's consistently strong across tasks. By not focusing on just one benchmark, Icons maintains broader capabilities. In the experiments, the authors test Icons on a large-scale dataset, proving that it reduces computational overhead while still picking out high-impact data. They compare it to other methods that are state-of-the-art, looking at both how well it performs on known tasks and how it transfers to tasks it hasn't seen before. Now we get to the results, comparing Icons against other data selection methods. If you look at the table here, you'll see that Icons comes out on top. It retains almost 99% of the full dataset's performance, even though it's using only 20% of the data. That's a big win for efficiency. They also compare Icons to approaches like coin-C-die and D2 pruning, and Icons outperforms them. This shows how well it generalizes across tasks and keeps high quality despite the reduced dataset size. The section also gives details on the task types and dataset sizes, showing that Icons can handle various scenarios effectively. Here, the authors continue evaluating Icons across a mix of benchmarks. They mention 6 categories of tasks, such as multiple choice understanding, visual question answering, and open-ended generation. Icons consistently equals or beats baseline methods, sometimes even matching the performance of training with the full dataset. Take a look at tasks like SQAI, MME, and POPE. Icons manages to stay right up there in accuracy and efficiency, despite cutting the dataset down to 20%. The discussion also delves into how Icons evolves from looking at each task's influence to a more universal view, ensuring the chosen data works well overall. Moving on, we see a direct comparison between specialist and generalist approaches to data selection. Specialist picks data based on single task influence, while generalist looks at overall influence across tasks. The table here shows that the generalist approach usually does better, keeping performance high across tasks with only small dips in certain benchmarks. You can also check out the figure Icons consistently beats the baselines at various sampling ratios. Even at 40% of the original dataset, Icons holds on to more than 99% of performance. And at 60%, it actually exceeds the full dataset's performance by 2%. That indicates a strong ability to weed out unhelpful data while keeping the crucial bits. Still on the specialist versus generalist theme, the takeaway is that Icons' generalist strategy outperforms simply focusing on single tasks. Using only 20% of task-specific data, Icons reaches near full dataset performance in tasks like SQAI and MME. There's an interesting overlap analysis too. Some tasks have a lot of shared data samples that are important, while simpler tasks have less overlap. Icons stands out especially at low sample selection ratios, filtering out noise and focusing on what matters. If you're curious, check the figure to see how tasks like VQA2 and VizWiz share more data. Others don't overlap much, hinting at unique data demands for those tasks. Here, the authors visualize the overlap between selected samples across different tasks and aggregation strategies. In one heat map, related tasks like POPE and GQA have a high overlap in the data they pick, while MMBench and GQA differ quite a bit. Another heat map compares how the vote-based consensus method aligns with approaches like mean and max. Those two are almost identical, whereas vote-based consensus picks a more diverse selection. These visual comparisons show that no single method or task coverage is perfect for everything. That's why Icons is structured to adapt to each task's nuances while still aiming for broad applicability. Now, we look at how well the selected training subset generalizes to tasks it wasn't trained on in the first place. Surprisingly, it does really well, sometimes even better than training on the full dataset. For instance, tasks like Info VQA and CMMMU see noticeable improvements. This indicates the subset truly catches the key concepts that matter for many tasks. The authors also test cross-architecture scale generalization, checking if the chosen subset still works on bigger models. The answer is yes. It remains effective even as models grow. This underscores that the selected data isn't just tied to one particular model size. Instead, it's got fundamental signals that help across the board. Next, the paper drills deeper into how Lava Icons -133K, the selected subset, fares in two crucial areas: unseen task generalization and scaling to different model sizes. On tasks never seen during training, the subset often matches or surpasses full data results. Look at tasks like Info VQA and Real-World QA, you'll see major gains. That suggests the chosen data captures key relationships that transfer across tasks. When they move on to bigger architectures, the subset still holds its own. The 7B model hits over 97% effectiveness, while the 13B model does even better. This consistency underscores that the chosen data subset can handle diverse scenarios. This part compares the voting-based consensus method with other ways of aggregating influence scores, like simply taking the average, picking the maximum, ranking samples, and normalizing. The vote approach achieves 98.6% overall performance, which is the best among these. Mean and max often pick similar samples, leading to high overlap, while vote seems to diversify the selection and cover more ground. They also show that focusing on consensus across tasks before picking samples leads to better results than merging task scores in a more direct way. By emphasizing consistency across tasks, the vote-based strategy avoids overfitting to a single task's validation data. Here, the authors compare consensus-aware methods with direct merge approaches. Consensus-aware focuses on aggregating scores across tasks first, whereas direct merge treats all validation data as one lump. Consensus-aware turns out to be more effective, offering better coverage of tricky tasks like MME. Then they categorize data selection strategies into representation-based, trajectory-based, and gradient-based methods. Icons fits in the gradient-based category, but stands out by using a majority voting scheme that doesn't assume anything about the relative difficulty of tasks. Finally, Icons addresses the limitations of previous approaches by applying a task-aware, voting-based influence consensus. It avoids problems caused by letting one task dominate the selection and can be updated for new tasks without too much extra computation. Achieving 98.6% of full performance with only 20% of the training data, it also transfers well to tasks and domains it hasn't seen before. Of course, the method isn't without constraints. Calculating gradients for huge datasets still costs a lot. That might limit its use for very large-scale data. However, the authors do release Lava Icons -133K to help researchers in lower resource settings. They also note connections to related work in visual instruction tuning, which focuses on building multimodal models that can understand and follow instructions. And that wraps up our exploration of icons, a method aiming to make vision language training more efficient by zeroing in on the data that truly matters. Thanks for tuning in to this deep dive. Hopefully, it's given you a clearer understanding of how icons can streamline your data selection and reduce training overhead. If you have more questions, feel free to explore the references or the supplementary materials. Best of luck with your experiments, and see you next time.